Many areas of science and engineering involve the calculus of vectors and matrices in high-dimensional spaces, like relativity, quantum mechanics, solid and fluid mechanics, electrodynamics, data science, and any field that deals with data in high-dimensional spaces. I have found in my own teaching that students are very good at the calculus of scalar quantities and functions, but the moment we move over to vectors and tensors, I just see deer in headlights and the letters WTF written all over the students' faces. And that was actually my experience being exposed to this subject as well. I remember the math professor going up to the front of the board and writing down the words, "A tensor is an object that transforms as a tensor." What are you talking about? That's not fair. You can't use a definition in a definition. Is this a class on philosophy or engineering? And I remember the professor basically saying, this is a tensor, here you go learn it. And maybe some of you share a similar experience as well. Today, I will introduce what a tensor is, at least my interpretation of what a tensor is. Again, it's philosophical, and a way to perform vector and tensor calculus using Einstein index notation, which saves an incredible amount of clutter and time and helps you focus on what really matters in an expression in a process. For the purposes of this video, I assume that you know what a vector is and how to take basic vector operations like the divergence of a vector. So let's suppose that we have a two-dimensional system denoted by the scalar quantities x and y along the horizontal and vertical. I have a position vector x denoted by an arrow above the variable. Another way to denote a vector is to put an underline underneath the variable, just like so. I will adopt this notation where I put an underline below the variable. This vector x contains two scalar quantities, x and y, which denotes the physical position along this two-dimensional system. Don't confuse this scalar quantity x with this vector quantity x. This vector quantity x is a container, it's a vector that contains two elements of scalars x and y that denote physical positions along this two-dimensional system. Another way to denote a vector is to use Einstein index notation, where I've replaced the underline with a subscript of letter I. And this I can take on the values of 1, which denotes the position along the x, or 2, which denotes the position along y. So whenever you see the variable x with a subscript I, that denotes a vector quantity where the value of your index will tell you whether you're pointing to the first entry of x or the second entry of y. If you don't like the letter I, you can choose any letter that you want. Pick your favorite one, J, N, M, K. It could be any letter. Okay? So technically, this subscript I could be written as a subscript or a superscript. And this is where it gets into the details of covariant and contravariant notation, which is very important when you're dealing with the change of basis. For example, in solid mechanics, where you have a deformation of a material. I think that as an introduction to vector and tensor calculus, the covariant and contravariant notation overcomplicates things. And I found it more helpful to just first learn the basics of Einstein notation and how to perform vector and tensor calculus just by using the subscript. So I'm going to stick with just a subscript. So whenever you see an index underneath a position variable x, that denotes a vector that carries an element, x and y, along this two-dimensional space. Now, I often tell my students that math is the language we use to communicate science and engineering. And the best way to learn language is to just start speaking. We can go through the detailed grammar and technical details of what the rules are for index notation and all the definitions that it has. I have found it more helpful to just start doing a bunch of examples. And as we do the examples, the rules will automatically come up. And as they come up, I will introduce them. So let's get started with just some basic examples. Let's suppose that I would like to calculate the gradient of some vector quantity x, the position vector as denoted over here. This gradient operator is the usual gradient operator in two dimensions, where we have the partial derivative with respect to x and along y contained within this vector. So note that this is not a simple dot product between this vector and this vector, which is what you would have if you had a dot in between them. That's the divergence of the position vector x. In this case, we have an outer product, otherwise known as a dyadic product, between two vectors. So it's not going to be a simple dot product. Another way to write this operation is the derivative of the position vector x with respect to another vector x. Okay? So you've probably seen in your calculus class that the derivative of the scalar function x with respect to x is just simply equal to 1. That's very easy. So you'll look at these two expressions and say, oh, well, this one looks very similar to that one. Maybe this is just also equal to 1. You're almost right, but there is a fancier version of a 1 that's going to come out through this operation. You'll see that come up right now. So let's use our Einstein index notation to rewrite this as partial of x and then partial of x. But because we have a vector on top, I'm going to first put one of the indices I up there because I replaced the vector position x with just x of I, shown here. And then the denominator, I'm going to have a different index j because this numerator x vector and this denominator x partial derivative can take on different values of the scalar positions x and y. So you need to keep those indices separate. Okay? So I can take on the values of 1 and 2, right? It can cycle over those two indices. And then also j can take on those two values as well. So j can be 1, j can be 2. So now let's just fill out these entries. If I is equal to 1 and j is equal to 1, then x sub 1 and j sub 1 will just tell me that I have both x and x. So I'm going to have partial of x, scalar x, relative to derivative of scalar x. If I is equal to 1, it's still going to be x on the numerator, but j is equal to 2, which will give me a y on the denominator. Okay? So the same thing here, if I have I equal to 2, now the numerator becomes y, and I'm going to differentiate that relative to scalar x. And lastly, when j is equal to 2 and I equal to 2, then we have partial y, partial y. Okay? So now every entry inside of here are scalars. So obviously, this is going to be equal to 1. That's going to be equal to 1 because you're taking the derivative of a function with respect to itself. So that has to be 1. But because x does not depend on y, this is going to be 0. And that's also going to be 0 because y doesn't depend on x. Okay? So what you've effectively done is to create a matrix of entries from this derivative operation. Okay? So this is a matrix that you're probably familiar with from your linear algebra class, where you have 1s along the diagonal and 0s along the off diagonal. That, as you recall, is called an identity matrix, which I'm going to denote with an I with 2 bars underneath. So whenever you have 2 lines underneath, that denotes a matrix, as opposed to 1 line underneath that denotes a vector. Okay? So in Einstein index notation, this identity matrix is denoted with the Greek symbol delta and then subscripts I, j. Okay? This is called a Kronecker delta function. Okay? And the Kronecker delta function works if I and j are equal to each other. So if you are either here on the upper left or on the bottom right, this value is equal to 1. And if I and j are not the same, so if you're lying along the off-diagonal elements, then this value is equal to 0. Okay? So it's just the same as the identity matrix. It's just represented using Einstein index notation. Okay? So notice that this solution ends up giving you a matrix. Okay? So far, so good. Now, let's do another example, an example that you're likely more familiar with. So let's suppose that I would like to calculate a quantity that is the divergence of the position vector x. So unlike the example we just did up here, where it was the gradient operator directly outer product with the position vector, this is the gradient operator dotted inner product with the position vector x. So another way to rewrite this is as the gradient operator acting as a dot product onto a position vector x. So here we come to an important rule in Einstein index notation. Whenever you have a dot product between two vectors, you repeat the same index. Okay? I are repeated. Up here, we used I and j, which were different indices, but here we use the same index. You can also choose the letter j as well, or k, or any index. This I is called a dummy index because it can be any index you want. They're repeated with each other. And the rule with Einstein index notation is that if you have a repeated index, you go through all possible indices and add them together. So the possibilities of the index I is that it can take on the value of 1 or 2. So let's cycle through both of those values and add them together. So the first index, I of 1, will give me x, just like that. And the rule is I need to add them together, right? So I'm going to take my I of 2, which now takes on the position y. So I've taken I of 1, I of 2, which are the two possibilities of this index I, wrote down the expression, and added them together. That's the rule of Einstein summation notation. Okay? So of course, in this particular case, this is very easy because that's equal to 1 plus 1, and the value is just equal to the number 2. Okay? In general, if we have a d-dimensional system, this value will just be equal to d, the number of dimensions in your system. Okay? Note what's kind of interesting is that this divergence of the position vector x, all it did was to take the diagonal entries of your matrix and added them together. Okay? So an alternative way to write this expression is as the trace of this matrix gradient of x. Okay? So what's kind of cool about Einstein index notation is that it tells you directly which elements you're going to add up together. So another way to write this is as the delta, Kronecker delta, of I. And that should make sense to you, because up here it was Kronecker of ij. So if we have the same index I and I, what that means is that when I and j are equal to each other, I'm just going to pick out those values only. So this entry up here and this entry down here on the bottom right. And of course, the sum of those two is the definition of the trace of the matrix. And in the two-dimensional system, we just get the value of 2. So what you'll notice is that in this case, what we found is a scalar quantity. Okay? So just as a summary of what we've learned so far, first, if you take the gradient of the position vector, you get a matrix to come out, delta ij. And then when you take the divergence of the vector x, we end up getting is a scalar quantity, which is equal to the number of dimensions in your system. So now that we have a scalar down here, we have an example of a vector and a matrix, it is the perfect time to introduce what the heck a tensor even is. Now that we have seen an example of a scalar, a vector, and a matrix, let's talk about what the heck a tensor even is. So my interpretation of a tensor is to think of a container of data, or container of numbers. And the size of that container depends on the order of the tensor. So for example, a 0th order tensor is the smallest tensor, and it has the smallest container, and it can only carry what we call a scalar. So let's say the common name of a 0th order tensor is what we call a scalar. And some examples of that, we've seen a bunch of them already, numbers like 1 or 2, scalar dimensions x and y coordinate, those are all examples of scalars. So the number 1, x and y, pi, e to the 10, those are all examples of scalars. And the analogy that I like to think about when I think of a 0th order tensor and a scalar is a single car parking lot. It's a small container that has just enough room to store one datum, right? One car, one piece of scalar can fit inside the small container. Now, let's talk about a first order tensor, which in common terms we call a vector. And we have already seen an example of a vector, which is a position vector. X contains the entries x and y. So you can already see that a first order tensor has a slightly bigger container. The size of that container is a little bit larger because now it contains data as a column vector. So continuing the analogy of car parking, this would be like a row of cars. Now the container is a little bit bigger. We can store cars along a 1D column. Okay, so it stores a little bit more data. Now, a second order tensor. This is an even larger container, and this is what we call a matrix. Okay? In the examples that we have seen so far, this is one example where we took the gradient of a position vector. Another example that you've seen was the identity tensor, right? The identity matrix. So let's just give some examples of that. So we had the gradient of a vector, which was an example of a second order tensor. We have seen the identity matrix with 2 lines underneath, right? The number of lines indicate which order tensor you are. So 0th order has no line, 1 line, first order tensor, 2 lines, second order tensor. And as a fluid mechanician myself, the most common example of a second order tensor that we see is a stress tensor denoted by the letter sigma. Okay? So continuing this analogy of car parking, this would be like a matrix of cars. So now I can not only store cars along a 1D axis, but now it's expanded into the second dimension. So I can park cars along this 2-dimensional space. Okay? So just as a note, whenever someone says this is a tensor quantity, people usually mean this guy right here as a second order tensor, as a matrix. Especially in fluid mechanics, whenever we say this is a tensor, we mean this guy. We would never call a vector a first order tensor or a scalar a 0th order tensor. You can if you want to sound super fancy, but it's unlikely that you'll come across those phrases used to explain a scalar and a vector. Now, if commonly we deal with third or fourth order or higher order tensors, if that comes up, people will specifically say this is a third order tensor or fourth order tensor. the word tensor is basically synonymous with this level, at least in my discipline of fluid mechanics, it's synonymous. It might be different in different disciplines. So now the next one is a third order tensor. And this, the common name of that, I think of as a 3D matrix. Okay? So this is kind of like a 3D matrix. And just to be clear, let's put 2D there to differentiate between a 2D matrix and a 3D matrix. Okay? So common examples of a 3D matrix might be an outer product of a vector, like a position vector, with a stress tensor. That's a third order tensor. Another example of that might be what's called a unit alternating tensor. I'll get into that a little bit later in the video, but it's a very important type of third order tensor that often explains chirality in a system. And chirality is super important in science and engineering. Life would be different without chirality in this world. So this is a very important third order tensor. And to continue the analogy of car parking, now you have no more space along the two-dimensional plane, and now you have to stack cars along the third dimension along Z. So now you have data stored not only along the X and Y, but you have data stored along the Z direction as well. So this is your 0th order, first, second, third order tensor. The higher the dimension, the more dimensions that the container has to store data. And you can, of course, keep going to 4th, 5th, 6th, and higher order dimensions. It becomes a little bit harder for me to explain and continue this car analogy because it's hard to picture what a 4th dimension looks like. But I think you get the point at this point. Now that we're starting to understand what tensors are just a little bit and using Einstein notation to do some basic calculations, let's do some more examples because more rules of Einstein notation will come up in further examples. So let's suppose that I would like to perform the divergence of the outer product of two position vectors x times x. So once again, this x times x is an outer product, not a simple dot product. So just as an aside, so whenever we have x vector dyadic into another x vector, that's not the same as x dotted into itself. Okay? So x dyadic x is equal to a matrix or a second order tensor, just like that. So you can see that they're clearly different. The second order tensor contains a lot more information than this 0th order tensor, also called a scalar. But you can see, interestingly, that the dot product is still just a summation of the diagonal entries of this second order tensor. So that still applies here as well. So in Einstein notation, this would be x sub I times x sub j. And of course, that is not equal to x sub I times x sub I. Because these are repeated, you sum over all possible values of I, which is 1 and 2. And then this one contains I that can separately be 1 and 2, and j that can also be separately be 1 and 2. So just by looking at the form of the expression, you already know what order of the tensor it is. This one has to be a 0th order tensor because all the indices are repeated. In this case, we have two separate indices. This product must be a second order tensor because there are two unique indices located here. Okay? So with that in mind, let's keep going with this example. If I rewrite this using Einstein index notation, this would be partial of partial xi of xi times xj. So you probably have noticed by now, but the order of an outer product of two vector really does matter. In this particular case, we just have a position vector which is identical to itself, so swapping them wouldn't really make a difference. But if I were to have a position vector, outer product with a velocity vector, like in fluid mechanics, the order really would matter. So if the velocity were to come here first, the gradient would apply in a different way. So the product of two vectors as a dyad, the order does matter. Okay, so now that we come to this form, the usual rules of calculus and product rules will apply. It will look just like this. So what's nice about this example is that this term, in this term, we've already worked out over there. So this is example number 1, this is example number 2. So let's fill those numbers in there. This one is a Kronecker delta function, ji, and this one is delta ii, which is equal to 2 for a two-dimensional system. Okay? So at this stage, we come to a very important rule in Einstein index notation. Whenever you have a Kronecker delta function of two indices, I and j, multiplied against another term that has the same, one of the same indices, in this case I is repeated, you swap the I and replace it with a j for this x of I. Okay? I've actually indicated the rule right here as well. Okay? So xi multiplied against the second order tensor delta ij becomes xj. So you swap the index from I to j. So ultimately, this term right here will just become x sub j, because I'm going to take the I, swap with the j. This one in 2D will become 2 times x sub j. So a couple of important notes here. Because I have a sum of two terms, this better be j, and this also better be j of the same index. If I have x of I plus 2 times x of j, something bad has happened because I didn't keep track of my indices properly. Whenever you're adding tensorial notations like this, they must be consistent with each other. So if you're still bugged by this index swap, think of your linear algebra class where you've learned the rule. Whenever you have an identity matrix times a vector itself, then it will just spit out the same vector. Okay? So this is kind of like your delta ji times xi, and this becomes xj. Okay? Just like your classic linear algebra class, but now using Einstein index notation. So ultimately what we find is that this answer is simply equal to 3 times the vector xj. So now if you still don't believe all of this and think, oh my gosh, this is so complicated, I know how to perform this directly, just using linear algebra, the classic tried and true methods, I'm just going to perform that and see what happens. Okay, so you can definitely do that. So let's do the old-fashioned method, where you just take this gradient operator, and it will just be, and then multiply against this matrix. Just like that. So then you use your usual linear algebra. The second row is acting on this one, and then this one. Okay? And of course, that is nothing but just 3 times your x vector. Okay? So now your answer here and your answer here are totally consistent with each other. So hopefully you believe the Einstein index notation a little bit more, but let's keep doing some more examples because we can identify more rules. Let's do an example that involves the use of the chain rule. Let's suppose I wanted to take the gradient of the magnitude of the position vector x inverse. Okay? So going over to the position vector, we can define a magnitude of this vector. Okay? So in index notation, the magnitude of the vector is simply the square root of xi times xi, because you're adding over index I, going from 1 to 2. And the way you might have known it from the radius of a circle might just be denoted by r. And that's equal to the square root of x squared plus y squared in scalar quantities of x and y. Okay, cool. So ultimately, what we would like to do is to solve. Good. So now we can use the chain rule. That looks just like this. Well, now we know that the radius r is simply given by this in Einstein notations. Let's write that in. Okay, so note that inside the numerator, I'm putting xj instead of xi, which is the way I defined it up here. I is a dummy index. J is also a dummy index in this case. But I'm avoiding the use of I here in this expression because I'm already using an I on the denominator. And here comes an important rule in Einstein index notation. You can only repeat an index once on any given term. If I were to put xi here, and another xi on the denominator, I will get confused on which terms I'm summing over. That would imply that I should sum over this I, and this I, but that's just not the right answer, because over here, we need to ultimately get a vector to come out, because it's a scalar quantity. This is the gradient of a scalar, which is a vector. So ultimately, I need this index I to survive at the end. So we don't want to sum over this xi on the denominator. That's why I'm avoiding the use of the I in the numerator and using a different dummy index j. Okay, so in Einstein index notation, for any given term, you can only repeat an index once. If, for example, there was another term that I added, there was a plus and another term here, I can again repeat the j over here because I'm not adding these j's with another added term j over here. So for any given term by itself, I can only repeat an index once. Okay? So at this stage, I can perform another chain rule. So let's do that. Okay? Just like so. Again, once more, I'm not using xj here. You might be tempted to use xj here because that's how it was up here, but I'm using xk and xk over here because I've already used j over here. If I have xj, another xj here, it would be totally confusing which terms I'm summing over. Good. So at this point, we know that this term is the Kronecker delta function, delta ik. That's going to swap this index k with I. Perfect. I can cancel out the 1/2 with the 2. This entity right here is just 1 over r, the magnitude of that position vector. So ultimately what I have is that this result, this is our final result. So when you take the gradient of the inverse of the magnitude of the position vector, you just get the negative of the vector divided by the radius cubed, the distance cubed. Now what's interesting about this result is that you can take more and more gradients of this 1 over x magnitude function. And it would look something like this. So what I have here on the top is just the exact same relation that I just showed. So the gradient of inverse r is just simply equal to the negative of the vector position xi divided by r cubed. You can do another gradient that's shown here, where you could just swap the interior of this term with the expression that we just found right here, and go through the more chain rules and more products rules using Einstein notation. It's actually not that bad. And you can keep going, right? You can do a third derivative over here on the very bottom. What's cool about this example is that this is a gradient that comes up very frequently in science and engineering. So for the chemists out there, the 1 over r function inside this operator, that is something like your s orbital. This term right here is your p orbital, this is your d orbital, and so on. Okay? For the physicists out there, the 1 over r is your monopole, this is your dipole, quadrupole, so on. People who do fluid mechanics, you can also see the analogy of your Stokes flow solution and then higher order moments of dipole, quadrupole, etc. This is called a multipole expansion, where each of these terms come out when you're solving these types of problems in electrodynamics, fluid mechanics, quantum mechanics. It comes up very frequently. And the reason why is that this 1 over r solution is a fundamental solution to the Laplace's PDE. And taking more gradients of that gets you more and more accuracy for different complex flows, different complex interactions between different point sources. So maybe I'll cover that during a different lecture, but this is just a really cool example where Einstein notation will help you make a lot of progress on calculating these gradients with a lot of higher order tensors. So this is a vector, but then you start to get second order tensor, third order tensors, and higher order tensors that quickly come up, where now keeping track of the tensorial nature becomes very challenging when you're using the old-fashioned vector tensor method and don't use the Einstein index notation. At this stage, I'd like to give a brief discussion about how Einstein index notation may be used to write common expressions that we see in our engineering classes. So these are two equations that we encounter, the Navier-Stokes equations and energy balances, in our engineering classes. And there's a term in the Navier-Stokes equations, which is a turbulence term, that looks like something like this. Okay? So if I were to use Einstein index notation to rewrite this expression, how would it look? So first, I have a v dotted into the gradient of another vector. So this would look something like, first, I take vi, which is that vector right there, and this is dotted into the gradient. See, we get that. And finally, this is acting on a different vector, v sub j. Okay? So now, the rule in Einstein index notation is that whenever I have a repeated index, I add them. So let's add them. v1, which represents x, I'm going to write x instead. The j stays, plus I have to sum over the second index, which is y. Okay? It will look something like this. So note that this entity right here, v sub j, is a vector, right? It's going to have an x and y component in a two-dimensional system. And I'm going to leave it like this for now, because ultimately this needs to give me a vector at the end. Okay? So now I can also rewrite this as just like that. So you can clearly see that this whole term right here is just v dotted into the gradient operator. Okay? And this v is simply the velocity that comes straight down. Okay? So Einstein index notation is a very convenient way of looking at terms that look somewhat intimidating when you look at it first, because you have a gradient of another vector. It looks kind of daunting when you first see it, but when you break it down into the notation, look at it carefully, it's not so daunting after all. Another term that we often encounter in our energy balance equation is a term that looks like the term here, which is the stress tensor sigma, which is a second order tensor, double dotted into the velocity gradient of v. So now we haven't talked about the double dot product yet. It's analogous to the dot product, which annihilated one underline on either side of it. The double dot product annihilates two bars underneath. So there's two bars here denoting a second order tensor. This is also a second order tensor. It annihilates two on each side. Therefore, this quantity at the end will give me a scalar. Okay? Let's see how that comes out in Einstein notation. So the stress tensor sigma has indices I and j. We need to sum over both indices I and j. Okay, it will look something like this. So now let's cycle over all possibilities of I and j. In a two-dimensional case, it's x and y. Okay, it will look something like this. So it's a sum over every possible component within this 2x2 matrix, multiplied against every component of this gradient of the velocity. And you add all the components together. So it's similar to the dot product, where you add together repeated index, just like so, but you do it for both indices I and j. Okay? So the Einstein index notation can also be used for these types of double dot products, or even triple dot products, and higher order dot products may also be used. Okay, let's do an example that involves the use of the product rule. Let's suppose that I would like to take the divergence of a dyadic between a second order tensor and a position vector x. So let's just think about what's the tensorial order of this final product. I have one dot product, which will annihilate one bar on each side. So that bar is annihilated, that one's annihilated, one of them is. So I have one left there, and I have the position vector, which is a dyad. So ultimately, this product at the end must give me a second order tensor. I should have two free indices at the end. Okay, so let's rewrite this using Einstein index notation. Okay, so I am summing over the index I. There, j and k are the free indices. Good, because I should have a second order tensor at the end. Now, let's just apply the product rule direct. Okay, it gives me this product. I just straightforward use of the product rule. Now, we know that this quantity is equal to delta ik. So I can just switch the indices between the I and the k. Okay, so then if I rewrite this back in vector form, I'll have this expression down here. Okay, so the divergence of a second order tensor times a position vector, dyadic on the interior, is equal to the stress tensor, second order tensor, plus the position vector, dyadic, with the divergence of the stress tensor. Notice how easy this was using Einstein index notation. If I were to try to take this divergence directly, I would be a little bit confused on what the heck is happening. Which thing is this gradient operator operating on? Is it the second index on sigma or x? It's all very confusing. But if you convert it over into Einstein notation, usual rules of calculus then apply, like the product rule. So it becomes very clear what you mean later on. And this particular calculation is very useful for me because I often make this calculation when doing viscosity calculations. In the field of fluid mechanics and rheology, there's this very famous calculation of the Einstein shear viscosity correction, where along one step in the calculation, you need to take this divergence. And you can already see that the divergence of the stress tensor is directly what's found in the momentum balance, in the Cauchy's momentum balance equation. So this is how we can make a lot of progress in the Einstein shear viscosity correction. So we'll see this calculation again in a different video. Another benefit of the Einstein index notation is that the notation of your operations are extremely clear. For example, let's suppose that we have a second order tensor, sigma. Now, if I wanted to calculate the transpose of this quantity, then all I would need to do is swap I and j. If you have a symmetric tensor, then it doesn't matter whether it's ji or ij. But in any case, the transpose of a second order tensor is more or less clear. But let's suppose that I wanted to take the transpose of this quantity on the inside. If I wanted to take that quantity, now it's not so clear what index I'm transposing over, because technically I have something that looks like this. But when you write this, it's not so clear whether I'm transposing I and j, or I and k, or j and k. It's all very confusing. Therefore, you would generally avoid the use of notation that looks something like this. Whenever you're taking the transpose, you would just use the Einstein notation directly and say, oh, for this transpose, I mean this. For example, you would just write the indice down directly without keeping it in vector and tensor form because transposes become very confusing. There are other examples where higher dimensional matrices and tensors become very confusing when you use the normal operators and normal operations, and converting it over index form makes it absolutely crisp what you mean about a particular operation. So this is another big advantage of using Einstein index notation. So far we've talked about vector derivatives, taking derivatives of vectors with respect to other vectors. But what about tensor derivatives? There are ways to take derivatives of tensors with respect to tensors. So let's suppose I would like to calculate this thing right here, the derivative of a second order tensor with respect to itself. So in Einstein notation, it would look like this. And so remember earlier that when I took partial x vector, we got an identity tensor that was just ones along the diagonal and zeros along the off diagonal. In analogy, this is just a higher dimensions of that. It would be 4 dimensions, I, j, k, l. Okay? So you would get, again, something that looks like the answer 1, but in 4-dimensional space. In this particular case, you would get this. It will be a product of 2 Kronecker delta functions of ik times jl. So as advertised, you get a 4th order tensor at the end of this. So with this rule in mind, let's do a couple of examples. I'd like to take the derivative of the inverse of this second order tensor sigma ij. So this is a little bit tricky. So let's consider a different identity first. Okay, this is just a fact. You probably have seen this from linear algebra. When you take a matrix, dot it into the inverse of its matrix, you get the identity. Okay. Okay, that's just writing the same thing in index notation. What I'm going to do is to now take this quantity and differentiate it with respect to sigma and m. Okay, using the product rule. I would get this, just straightforward application of the product rule. And I can use the rule for this. It looks like this. And ultimately, I'm interested in this quantity here because that's the ultimate goal, to get the tensor derivative of sigma inverse with respect to sigma. So I can now isolate this term. Okay, so what I've done here is I have first just taken this term, moved it over onto this side of the equation, and then I've just taken the inverse of this quantity. So be careful, whenever you're taking left inverse, you're going to have to swap the I and k with the k and I here. But ultimately, you arrive at this expression. Ultimately, I can just swap this I with an n, this k with an m, and you arrive at your final expression. So just as a final note, this is often encountered in situations like solid mechanics, where people will oftentimes differentiate between lowercase subscripts and uppercase subscripts to denote before and after deformation. I'm being a little bit cavalier with that without differentiating before and after deformation, just for the purposes of going through these exercises. But just note that in some situations you might come across, you'll have an index here that might be capitalized or lowercase depending on what operation you're trying to make within that system. At this stage, I'd like to introduce a third order tensor called the unit alternating tensor. It's denoted by a third order tensor with 3 indices, I, j, and k. So it would have 3 bars underneath because it's a third order tensor. It's very commonly used in 3-dimensional systems in continuum mechanics to indicate chirality. So the rule with this entity is that the indices I, j, and k, for example in 3D, could take on the indices 1, 2, or 3, right? So I can be 1, 2, or 3, j can be 1, 2, or 3, k could be 1, 2, or 3. So whenever the combination of I, j, and k is going in the forward direction, it's going to have a value of +1. whenever you're going in the opposite direction, it's going to have a value of -1. So for example, if I have epsilon 1, 2, 3, this is going to have a value of +1. If I have epsilon, that's also +1. But 1, 3, 2, for example, this is going to carry a value of -1. And all other cases where you have any repeating index, the value is equal to 0. And so on. Okay? So it's analogous to the Kronecker delta function, which was a second-order tensor with ones along the diagonal. The unit alternating tensor is an isotropic third-order tensor with ones in interesting locations. This is like the parking lot, where you have ones along specific positions moving in the forward direction when your indices cycle in the positive direction. And it has a value of -1 when it cycles in the opposite direction. It's a parking structures where different entries have zeros, ones, or -1s. Okay? So common uses of this Kronecker delta function include many examples that involve chirality. So the cross product, let's talk about that. Let's suppose that we have the cross product between some vector q and another vector omega. Okay? And the time symbol means a cross product. So the way to write this in Einstein index notation involves the use of this unit alternating tensor. It looks something like this. So I have the vector qi, vector omega j, that gets cycled through epsilon ijk, and out comes k as the free index. So what it's actually doing is taking two vectors and spitting it out in the orthogonal direction to both vectors. So it also has chirality because you can see that it can carry a value of plus or -1. So it matters whether you're going in the positive or negative direction. It's got handedness to it. Okay? And cross product does have handedness to them. An important relation that involves the dot product of two unit alternating tensors is called the epsilon delta relation. Okay, so the dot product between two unit alternating tensors. So I have one repeated index n that's repeated, so you have to sum over them. But it turns out that you can write this product of two epsilon unit alternating tensors as, okay, just like this. So what I've done is to take the first index I with k, create a delta ik, j and l, create another delta, minus the other two combinations, so I and L, J and K. So this is a useful relation that comes up in a lot of applications, like you'll see at the end of this video. As a final example of vector and tensor calculus, I'd like to provide an actual science and engineering application that will show you how powerful it is to know how to use Einstein notation, because it will make this calculation a lot easier than if you don't use it. So let's suppose that we have some object in three-dimensional space, and we place a little red dot on it to indicate its orientation as a function of time. So this vector, unit vector q, has components given by theta and phi, which is the angle in three-dimensional spherical polar coordinates. And let's suppose that this object is subject to some kind of random noise. Maybe it's a drone that's flying in the sky that has some random noise from the surrounding environments, or there's some kind of electrical noise that will cause it to fluctuate and rotate in space. Or it could be some kind of particle suspended in a fluid that's subject to some thermal kicks from the surrounding solvent. Okay, so for whatever reason, there's some kind of noise that will cause the particle to rotate in three-dimensional space. And our goal was to figure out how that dot, indicating the orientation vector, relaxes or changes as a function of time. And the equations of motion that governs how this orientation changes and spins around as a function of time is given by the following equation. On the right-hand side, we have a vector, lambda, which is called a random noise vector. And this random noise vector has the following statistics. This is commonly called white noise distribution or white noise statistics, and it is a vector carrying a bunch of random numbers that are drawn from a distribution. And that distribution has a mean of 0, which means that all the entries inside this vector, on average, will be a value of 0. However, its width of this distribution is given by the second expression right here. So it has a value of 1. So this delta function, t minus t prime, indicates that the random numbers that you are pulling from at some time t is completely uncorrelated with a distribution at a different time t prime. Okay, so you're always pulling from a fresh batch of distribution, and they're not related to each other over time. And finally, you have this identity matrix, which you already know about. It's just a ones along the diagonal and then zeros on the off diagonal. Now, you can think of it as this object is subject to this random noise at every time step t. It's going to be amplified by a prefactor, which just gives you the magnitude of that noise. And finally, that's going to result in an angular velocity on this object. Okay? So now there's some object in an environment that's applying some kind of noise. The noise is pulled from white noise statistics. At every time t, it receives some kick. It's amplified by this magnitude and ultimately transmits as an angular velocity that causes this object to spin around. Now, what's the relationship between the angular velocity and the orientation vector q? Now, we can use a relation called the kinematic condition, which is given by the following expression. So the time rate of change of the orientation vector q is simply given by the vector q cross product with the angular velocity omega. So we can combine this equation of motion to the omega down here, and all we have, we get an expression that looks something like this. And this is our main equation of motion that will tell you how a random noise vector gets turned and applied onto an orientation vector q, amplified by some known amount, so dr is a known value to you, and gets changed by the time rate of change of the orientation vector q. So this is an example of a stochastic differential equation. And in this situation, Einstein notation will really help us solve this equation. So for now, let's just work with this equation as the main equation. Okay, so now I've put our governing equation up here and the statistics about the lambda random noise vector up here on the upper right. So now let's put this equation using our knowledge of Einstein notation using indices. Okay, so what I've done here is to represent the cross product as qi lambda j epsilon ijk, just like I told you earlier about the cross product. We have a free index k that needs to be preserved on the left-hand side as well. So the tensorial order of this equation is a vector on the left-hand side and also a vector on the right-hand side, which always has to be preserved. Good. So now when you look at this equation, what you can notice is I have a q, which is the variable I'm trying to solve for on the left-hand side, and then a q over here on the right-hand side as well, and then some function of time over on the right-hand side. That's kind of like a coefficient. So now, this is analogous to a very easy equation that all of us are used to solving from classical calculus. An equation, a first-order equation, looks something like this. dy dt is equal to some coefficient matrix A of t times y of t. Well, now that has a very simple solution. You can separate the variables and then integrate both sides. And you get a solution that looks like y of t is equal to the initial condition y of 0 times an exponential of the integral of your coefficient over time. Okay? So if you look at it, this has a very similar form. So maybe we can write a similar solution to the one over here, as long as we are careful about preserving our index. So let's give it a try. Looks just like that. You can clearly see that the solution looks just like the solution that you probably already know how to solve, like the one on the bottom right, except you have to be careful with your indices. So we have an integral over your random noise vector, lambda j, and that's contracted with the j term here. The k has to come outside and preserved on both sides of the equation, and the I needs to be contracted over this initial condition I. So now we preserve the tensorial nature on both sides. Okay, so let's get rid of that. And the initial question that I asked is I would like to know how this orientation vector on this object decorrelates or forgets about its initial condition over time. To do that, I would like to multiply this answer, both sides, by the initial orientation. Let's go ahead and do that. Okay, so it looks something like this. Now all I've done is to multiply the answer that I had before with itself, taking the dot product, so it's essentially contracted over this index k. But importantly, I've multiplied against this orientation vector at initial time t of 0. And I want to observe how this later orientation vector, how it's related to its initial orientation. So now I would like to take the average to take a proper correlation. Okay, so I'm going to take correlation between the left-hand side, and the initial orientation vectors is just a constant vector, so there's no need to include them in the averaging. Okay, looks something like this. Good. So now this expression should presumably contain information about how the direction that this object is pointing at some time t equals 0 is related to how it's pointing later in time, q of t. Okay? So at this stage, we can do a Taylor expansion on this exponential term, making sure that we keep track of the tensorial nature in the indices I and k, so that they dot into this I and k and ultimately give us a scalar. So let's go ahead and do that. Okay, I know it's a very long expression, but this looks just like a normal Taylor expansion of an exponential. 1 plus x divided by 1 factorial plus x squared divided by 2 factorial and dot dot dot, which includes higher order terms. Of course, the 1 has to be a second order tensor because this quantity right here has the indices I and k that are alone, whereas j is summed up. Therefore, I have I and k, which stands in for 1, and this I and k is repeated over this I and k such that they ultimately will give you a scalar, which must be the case because the left-hand side here is summed over k, and there's no free index, and it must give us a scalar. The second term here represents x, so I have ijk, j is repeated, and therefore I and k are free. And of course, we're taking the bracket, the average of this term. So the average of the identity tensor is just itself, so there's nothing to average over there. That term needs to be averaged. And secondly, this term needs to be averaged, just like that. Okay? So you can Taylor expand an exponential, just as you normally would, and then the averages will pass through to each of the individual terms. So as we showed earlier with the white noise statistics, the average of this random noise vector must be equal to 0. Okay, so that's identically equal to 0. And the variance of that noise is given by this expression right here. So ultimately, this expression right here something that looks just like that. So at this stage, we have a long, ugly expression, but using the statistics of the noise vector, we can make a lot of progress. Okay? So the only tricky thing about this expression might be, when you do the Taylor expansion, this one should look like a term that's x squared. And when you do x squared, I'm taking one of them, which is epsilon ij, what used to be a k, but that has to be left behind at the very end when you take the other x product of the quadratic x squared term. And therefore, it's ijn dotted, so n is repeated, mk. And then this random noise vector dots into the middle indice there, and that random noise is dotted into this middle index for epsilon n mk. Okay? So as I said earlier, there's this interesting relation called the epsilon delta relation, where you can write this term as a difference between Kronecker delta products. Okay, so let's do that too. Okay, looks just like that. So now we can use the sifting property of a delta function in this integral, right? So whenever you have a delta function, you integrate it, you swap the function that's multiplied in the integrand with the argument inside the delta function. So in this case, you would swap t prime with t double prime, but since there's no other function that's multiplying it, it's just the function 1. So then this inner integral will just give us the function 1. This outer integral over t double prime would just give us time t, because you're integrating the function 1 over dt. So this whole integral will just give us time t. And then ultimately, you can just use this Kronecker delta function that swaps any repeated index with the other one to simplify the product of these two expressions. So let's go ahead and do that. And secondly, this one over here, I have ik jm. This jm will replace this one, so I'll have delta jj or mm. The dummy index can be any variable. So in 3 dimensions, this is going to be 3 delta ik. Okay, and then this integral will give us time. Okay, so let's clean this up a bit, and I'll rewrite it to where we are now because it's getting a little bit messy. Okay, so now I have simplified this long, ugly expression at the bottom and just rewrote it up here. Okay, so I have, again, the correlation between a vector at time t correlated against itself from initial time, is equal to the product of two vectors, orientation vectors at initial time, times this infinite series, okay? Where this is basically 1, a fancy way of writing 1, a tensor way of writing 1, minus 2 times the magnitude of the reorientation noise times the identity times the time plus higher order terms. Now, if you were to include the higher order terms, what would happen is that every odd term on the Taylor expansion for the exponential will always have a term that is the average of the noise vector. Those all go away. So only the even expansion terms of your Taylor expansion for your exponential will stay. And what we will find is that the next term down here will be like this term squared divided by 2 factorial. So this in itself looks like an exponential Taylor expansion. So what you can do is to write this term entirely here as just like that. So I've factored out the delta ik because it's going to be common in every single term. And e to the negative 2 drt, if you were to Taylor expand that out, you would exactly get 1 minus 2 drt plus higher order terms. And this is exact. You'll exactly find this if you were to work out the integrals and the expansions for the higher order terms. So now this is very interesting. We're almost done. So now you can replace this I and k using the swapping, right? So we have here I, k. So you swap it and you get. So now the orientation vector q is a unit vector. So this is just 2 unit vectors dotted into each other, okay? And that's just the magnitude of the vector, which is equal to 1. So in this particular case, this prefactor is exactly just equal to 1. Okay, so now we are finally done. We now know exactly how an orientation vector decorrelates as a function of time. So of course, this is just a vector dot producted into each other. So let's revert it back to the full vector notation. We have and just like that, we have our final result. So apparently, whenever we have an object in 3D space, and it's subject to some kind of noise that will cause it to fluctuate and rotate and jiggle around, if you track that unit orientation vector and see where it goes, at some later time t, when multiplied with its initial time, is going to decay exponentially quickly and is weighted by how large the magnitude of that noise actually is. And so if I were to plot this solution, it would look something like this. So along the y-axis, I'm plotting q dotted into q at initial time. And on the x-axis, I'm plotting time t. So of course, it just looks like a simple exponential decay, where it starts at time t equals 0, which is 1, meaning that time t equals 0, the two vectors are perfectly correlated with each other. There's perfect memory of which direction you're pointing in. At some later time, you see that the perfect memory goes away, because at some later time, you're kind of forgetting where you used to be pointing some time ago. And you can see that as a function of different values of this magnitude d sub r, you get different rates of decay. So if you have a small value of dr, you retain a lot of your memory because the magnitude of the noise is small. But as you increase the magnitude of this dr, then it means that you're subject to a lot more noise, and therefore you forget about your past even sooner. And so this is how an object would decorrelate in its angle over time. So a graphical illustration of this is you have some object that's pointing in this direction at time t equals 0. At one time step later, it's pointing in this direction. Much later time, it's pointing in this direction down. So at this stage, when it's pointing down, it's completely forgotten which direction it was pointing initially. And that's where you go from the memory of 1 all the way down to 0. And it depends on how strong your noise is affecting the rotation of your object. I like this example as a demonstration of Einstein index notation because there were a lot of steps along the way where if you didn't know the Einstein index notation, it would be a very challenging calculation to make. And what's nice about the Einstein index notation is that whenever you can put it into this index form, you can pull a lot of the classical tricks from standard calculus and algebra and apply them directly to your calculations. Whereas if you keep it in vector and tensor form, it becomes a little tricky to know what exactly you're operating over. So a real application of this result might be of a motile bacterium swimming around in solution. As the bacteria swims in one direction, it's unbundling its flagella, it's swimming, and after some time, due to noise from the surrounding solvent, it will slightly turn over time, and then some later time, it will forget which way it was pointing a long time ago. And of course, it's going to depend on how strongly the noise is affecting the direction it's swimming in.